Hi, this is Lee. I'm going to show you another subsystem on the TRILLSAT prototype that I've been working on. This is the gyroscope. I use it as an experimental inertial stabilizer. And what it is that there's a wheel inside the battery box here, or the battery frame, and it's driven by a BLDC motor, which I extracted from a DVD drive. It uses an L6234 motor driver chip and an LM339 quad comparator to read the 3 Hall effect sensors, and I drive it via PWM using an ATtiny1634 microcontroller via its 8-bit hardware timer. Now, I've shown the motor working outside of the craft, but I've never shown it working on the tether. I'm going to go ahead and ramp it up to 360 RPM, but first I'm going to start it at 280 RPM using a gyro 7 command. The 7, if you just multiply that by 40, you get the RPM, and then after that gets up to speed, I'm going to ramp it up to 360 RPM using gyro set RPM, which sets it on the fly. And I'm going to issue a gyro stop to shut it down if anything goes wrong. The first thing I've done is I set the series mode of the batteries so that it raises the voltage to over the nominal 7.2 volts. The motor driver IC needs a higher voltage, and the motor itself likes the higher voltage. And if I don't do that, actually, the chip will short out the pins on the ATtiny1634. It will just ground them. So I have to make sure I get that. I actually have code set up to do that in case I forget. So what I'm going to do is show you the reason for it. It's a solar tracker, and as you see, because the solar tracker is on a tether, if there's any kind of wind or motor vibration from the capstan drive, it will start to lose alignment with the sun. So the experiment was to see if I could add the inertial stabilizer that would keep it from rotating and allow it maybe to swing like this, but still maintain solar alignment. And if the amount of energy received from the accurate solar alignment was greater than the amount used by the motor, then it would be beneficial. I don't know if that's going to be the case, and there are still some different ways I can drive the motor, but this was just an experiment. There is one problem with this design, though. The craft isn't balanced properly. It became too heavy for me, and I didn't intend it to be this way. What's happened is the weight underneath the craft is much heavier than the weight above the craft. I actually installed the batteries along the axis, thinking they would weight down the craft. So I put them in a neutral alignment. But what I should have actually done was raise some mass above this axis. I can still add offsets later, but there's a weird feedback effect that occurs with the planetary mass. It has to be larger to tilt it if the weight of the craft is heavier. So I need to lighten the weight of the craft. So it would be more effective if the craft was balanced and lighter, but for right now, this is all I've got. So what I'm going to do is just show you again. Okay, this is what happens without the gyro. I'm going to issue the command to turn it on. Gyro 7. Typing with my left hand. Alright, as you can hear, the BLDC motor is on, and PWM is on, and it's gradually ramping up, and it should stabilize at 280 RPM. And I've got it to ramp slowly because the the point of the gyro wasn't to cause any type of rotation when it's accelerating. I want it just to get to a set speed, and then it acts like the inertial stabilizer. But it could act to counter the rotation of the capstan motor in some arrangements. So I'm just going to let the thing get up to speed. I'm going to bring this down here so you can hear it. Again, the wheel that's rotating is inside here, and there's also a fan built into the wheel. So there are fan blades there that can allow it to act as a cooling fan at lower RPMs when it's not in the stabilizing mode. One of the things I worry about when I run the gyro is that the thing could break apart, because the thing's printed out of 3D printed out of PETG plastic. So at very high RPMs, the tensile strength is pretty good, but it could break apart. So the batteries are mounted just above the gyro wheel. However, I've separated the batteries from the wheel with a piece of aluminum sheet metal, just in case the thing breaks apart. And the aluminum sheet metal also allows me to cool the batteries using the fan. So it's still increasing in RPM because the pitch is increasing. And the microcontroller is monitoring the RPM using the Hall effect sensors. Okay, this always makes me nervous. Okay, it's reached 280 RPM and it's stabilized. And so what I'm going to do now is send a gyro set RPM 9 command. Let me use my other hand this time. Okay, and once I hit that, it's going to boost it to 360 RPM. There it goes. So it's running at 360 RPM. I don't want to run it any faster. Let's just see what happens. I'm going to tilt it. This time the characteristics of the swing are a little different. So I'd have to run it faster to get a larger effect, and I don't want to do that right now. Because I want to show you other subsystem of the craft before it breaks. Okay, I'm going to go ahead and You know, right now, it doesn't have much of an effect. That's interesting. Huh? I'm going to go ahead and shut it down. I pasted the gyro stop. I hit the gyro stop. And now it's just spinning to a stop. It takes a while for it to spin to a stop. So anyway, that's the inertial Gyrofan, and it's experimental, and I'm going to raise it to a higher RPM in the future, and I'll show you additional subsystems in other videos. Thanks a lot.